Good morning. Myself, Dr. C. Senthil Kumar, Professor and Course Coordinator, Department of Physics of Vinayaga Missions Kirbananda Warrior Engineering College, a constituent college of Vinayaga Missions Research Foundation, deemed to be University, Salem. So today we are going to discuss about laser. So what is meant by laser? So laser finds many applications in various disciplines. For example, engineering, communication, medicine, etc. So it is inevitable to avoid the study of laser. So in this lecture, we are going to discuss about what are the fundamental concepts of laser and what are the types of laser, what are the applications of laser in detail. So to know the basic concepts about laser, so we should first understand the two major branches of physics. So generally, physical principles or physical concepts are governed by Newtonian laws, which is the fundamental of physics. But these Newtonian laws are not valid in all the domains. For example, let us change the length dimension. So in around the range, in the nanometer range, 10 power minus 9 meter. So in the range around 10 power minus 9 meter, which is commonly called nano range, the classical laws are not valid. And below this range, we need to go to the quantum mechanical aspects. So where the Newtonian laws are not valid. So we should keep in mind when we go study the atomic structure or nuclear physics and all, the classical physics and Newtonian laws are not valid. So to know about the difference between classical and quantum concepts, where all the physical parameters are continuous. So in classical range, all the physical parameters are continuous, while in quantum range, all the parameters are not continuous, they are discrete. For example, energy is continuous in classical range, while energy is discrete in quantum range. So what is meant by discrete? So energy can take the value of either 1 electron volt or 2 electron volt. It cannot have any value in between 1 and 2. But in classical range, so it is always possible to have a value of 1 electron volt or 2 electron volt or 1.5 or 1.005 like that. So any value, any continuous value, it is possible in classical limit, but in quantum limit, so it is discontinuous or discrete. So generally, it is said energy is discretized or quantized. So let us consider energy levels. So these energy levels are not new. So if you consider the atomic structure, so we have atom, so it is nucleus of the atom, and the electrons revolve around the nucleus in some specific orbits. So first orbit, second orbit, like that. So electrons will remain either in the first orbit or in the second orbit or third orbit, like that. And the electrons are not allowed to lie in between any two levels. Either the electron can remain in the first or in the second orbit, like that. So also atoms are also having some energy. They also lie in some energy levels. So they will have some energy. So based upon that, we consider, for example, we consider only two energy levels. I consider either an atom or electron. So to begin with, we consider only two energy levels and either an atom or electron. So I consider an atom or electron like that. So the lower level is called ground state and the higher level is called excited state. We assume there is an atom in the ground level or there is an electron in the ground level. So my question is, what will happen to the electron? Whether it will remain in the ground level for longer time or it can go to the higher level, that is our big question. So we consider only two levels. The lower level you can name it as E1, and the higher level it is E2 to begin with, and I consider either an atom or electron and the ground level. So it is not possible for an atom or electron to go to the higher level. By nature it is impossible. So what we have to do? We have to give some energy. So only by giving external energy, the atom can absorb that energy and go to the higher level. Otherwise, the atom will remain in the ground level for longer time. Okay. Now what we are doing? We are giving some energy. In this example, we are giving energy in the form of light photon. So what happens? The atom absorbs that energy. The atom absorbs that energy. See here, the atom absorbs that energy and jumps to the higher level. So now, after absorption, the atom or electron is in the higher energy state or excited state. So this is the fundamental concept which happens in the atomic or electronic level. Next, in this case, we consider the atom in the higher level. So we have two electronic levels or atomic level. The atom is in the higher state. So in this case, in the second case, what will happen? How long the atom will be in the higher level? So by nature, we should understand any object, any atom, any molecule, any planet, everything want to try to occupy a low energy state. So just we also follow that principle only. So in daytime we are working and evening hours, night hours, we want to take some rest. So in the universe, everything want to take the lower energy state. So even though it is lying in higher level for some time, after some time, it is quite natural to occupy a low energy state. So coming to our example, we considered the atom or electron is in the higher state. So what will happen? So naturally, the atom will come down to the lower state. The atom is jumping to the lower state after some time. Okay, so the atom has come down to the lower state. Now what happens? There will be some extra energy. So since it is coming to the lower state, the extra energy should be released. So in our case, the extra energy is released in the form of a photon or light. Okay, next coming to the third case, here also I consider the atom is in the higher level. But my aim is I want the atom to come down whenever I require. So I want to specify the time in this case. So if I want to make the atom to come down to the ground state or lower energy state, what can I do? I can give some photon of energy h nu. So what will happen? Just by seeing this photon, the atom will immediately come down to the ground state. But in this case, we have 2 photons are released, and these 2 photons are coherent. So let us have a quick look of what we have discussed. In the first case, the atom is in the lower level and it absorbs some energy and goes to the higher state. This process is called absorption. And in the second case, we consider the atom is in the higher level and it is coming down by emitting some energy, and it is called emission process. It is called spontaneous emission because it happens automatically. And in third case, we are making the atom to come down to the ground state by giving some energy. In this case also, the atom is coming down to the ground state and emitting photon, but we call it as stimulated emission. Stimulate means we are inducing the atom to come down to the ground state. So spontaneous emission, which is occurring naturally, it will automatically happen. We don't know when it will occur, but in stimulated emission, we can give a precise time for the emission to take place. At what time? At what time I require, I can make the atom to come down to the ground state. So in this case, we obtain 2 photons, and these 2 photons are coherent. So we will see what is meant by coherent. If 2 waves are said to be coherent, so they should satisfy these 3 properties. What are the properties? They should have same amplitude, they should have same frequency, they should travel in phase. So in the diagram, we can see a transverse wave. So what is meant by amplitude? So amplitude is nothing but maximum displacement. So in this case, so they have marked, this is the amplitude. So the maximum displacement is known as amplitude. In our example, the first wave and the second wave are having equal amplitude. So they satisfy the first property, so they have same amplitude. Then coming to the second one, they should have same frequency. What is meant by frequency? It is nothing but the number of cycles made in 1 second or number of cycles per second. For example, I specify the time. In one second, it is making 1 cycle. Then the frequency will be 1. So suppose in 0.5 seconds it is making 1 cycle, we call the frequency to be 2. So here also the both waves are traveling at with same frequency. For see the curve, so they are having same frequency. For example, in 0.5 seconds, both are completing one cycle, and 1 second they are completing the 2 cycles. So they have same frequency. So this is also satisfied. Next, third and important property is in phase. So these 2 waves should travel in phase. In phase means what? So for that I want to specify an example. So in Republic Day parade, the military people are making march fast. So if you closely observe them, so if the first person is taking his hand to the front, all the other people are also moving, synchronizing with him. So all the other people are taking their right hand to the front side. So if you move the right leg to the front side, all the other people will move front side. So this is what they are walking in phase. Suppose the first person is moving his hand front, the second one is moving his right hand to the back. So they are in out of phase. So coming to our example, so what happens? The first wave is going to the maximum at a particular time, means second is also going to the maximum. So after some time it is going to 0. See, the second one is also going to 0. So if the first one is going to negative maximum, second is also following that, at the same time it is also going to the negative maximum. So definitely these two waves are in phase. So we also see what is the example for out of phase. So if I draw first wave like this, I call it as A. Then the second wave will be like that. So this is the example for out of phase. But what we require for a coherent property, all the waves should be in phase. So the source 1 and source 2 are in phase. So all the three properties are satisfied. I can claim these two waves are coherent. And this is the property we observe from the two photons emitted through stimulated emission. Another important thing we need for laser to happen, to generate laser, we need more atoms in the higher level. So only then we can stimulate the atoms to come down to the lower state. But in nature, what happens? You can find more number of atoms in the ground state and only less number of atoms in the excited state. So in this example we have given around 3 atoms, more than 10 atoms in the ground state. So this is quite natural. So if you observe any atom, if I take some atoms and immediately observe, generally more number of atoms or electrons will be in the ground state. But to generate laser, we need more number of atoms in the excited state. So see, in this example, we have more atoms in the excited state. Here we have only around 3 atoms in the ground state in this example, more than 10 atoms in the excited state. So this kind of state, we call it as population inversion. And this is the requirement to generate laser. So if you want to generate laser, you need more number of atoms in the higher state. So how to make the atoms to go to the higher level? So we have to give some energy. That is the only possibility. The atoms or electrons, they cannot themselves go to the higher state. We have to give some external energy. This process is called pumping. So there are different types of pumping. Optical pumping is there. Direct electron excitation through electric discharge method, it is possible. Inelastic atomic collisions, we can make the atoms to go to the higher level. Direct conversion is there. Through some chemical process it is possible. So these are the different methodologies, and we are going to discuss few of these pumping process. So now coming to the concept of laser. So we consider the atom is in the excited state and we send a light photon. Just by observing what happens in stimulated emission, we get 2 photons as a result. And these 2 photons interact with 2 other atoms. We obtain 4 photons, and these 4 photons interact with 4 other atoms in the excited state. Again we get 8 photons like that. So just they are multiplying. So finally we obtain a intense beam of laser. So this is the fundamental concept which is common for all the types of lasers. So anyway, we are going to see one by one different kinds of laser. So the laser, the word we are using, it is an acronym. So what is meant by acronym? It is the short form of a long sentence. So laser, the expansion of laser is light amplification by stimulated emission of radiation. So we capture the first letter of each word, we get the word laser. Some other examples, we have Indian Space Research Organization, we call it as ISRO. So some of the important characteristics of laser we see, first one is high directionality. So normally we play with laser light. So in presentation, PowerPoint presentation also laser light is being used. So what is the difference? In ordinary light, the light beam will get diverged. But in laser beam, so they are highly directional, they don't diverge. So from this diagram we can see. So the laser takes a straight line path. But what happens in the case of this ordinary light, this light beam is diverging. See, so it is going like this. So next one is intense beam. It is extremely intense beam. So how to explain about intensity? It is the number of photons passing through unit area in unit time. So if you verify, so what is the number of photons in laser light? It is very, very high when compared to the ordinary light. So this beam is very powerful. And the third important property is high monochromaticity. So if you see the wavelength profile of a laser light, it is very, very sharp. So you can see this. So if you plot this, it is very sharp like this. But if you see the ordinary source, it is localized around a central region. So this is what we have drawn in this diagram. So we have both wavelength profile of laser, which is a sharp thing, and the wavelength profile of a ordinary source. Next, and very important property is the laser light photons are coherent. We have already seen what is the property of coherent. So they should have same amplitude, same frequency, and they should be in phase. So there will be billions and billions of light photons in a laser beam. All of them, if you pick up any two, they will satisfy the property, the coherence. Now, let us generalize what we have discussed earlier. So the three quantum mechanical processes, absorption, spontaneous emission, stimulated emission, are happening continuously if you take an assembly of atoms. So let us consider an assembly of atom which is in thermal equilibrium at temperature. So according to Maxwell-Boltzmann distribution law, we can specify what will be the number of atoms at a given level, given energy level. So that is specified as n equal to n0 into e power minus e by kT. So n0 is the number of atoms in the ground level, and if I want to know the number of atoms in the particular level E, so it is given by Maxwell-Boltzmann distribution. Okay, so from this derivation, from this expression, I can easily specify what will be the number of atoms in the level E1 or what will be the number of atoms in the level E2. So for example, if I want to know the number of atoms in the level E1, so that is given by N1, which is equal to N0 into e power minus E1 by kT. where K is the Boltzmann constant, T is the temperature. Okay, now I want to know what is the number of atoms in the level E2. How to find that? Again I can write N2 equal to N0 to e power minus E2 by KT. So it is very simple. So similarly I can tell what is the number of atoms in the level E3, E4, like that. So everything is possible through this Boltzmann distribution law. So I will consider only these two levels, E1 and E2 only for our example, and I use this relation and divide the first relation by the second relation. I obtain an expression for N1 by N2. So if I divide, what will happen? N1 by N2 equal to e power h nu by kT. Now we form some relations for the quantum mechanical process which we have discussed earlier for absorption. What is the number of absorption transition happening per unit time? So I can give through a relation R AB is equal to N1. N1 is the number of atoms in the level E1 and B12 is the probability of absorption transition and Q is the energy density we are giving. So for absorption process we have to feed some external energy, that is Q. Similarly for spontaneous emission, what is the number of spontaneous emission process happening per unit time? That is given by RSP equal to N2 into A21. N2 is number of atoms in the level E2 and A21 is the probability of spontaneous transition. A similar expression we obtain for the stimulated emission transition. Number of stimulated emission transition taking place per unit time per second per unit volume. It is RST equal to N2 into B21 into Q. Again B21 is the probability of stimulated transition. One thing we have to note here is only for absorption and stimulated emission we need external energy, but for spontaneous emission there is no external energy term, that is there is no Q term in this relation, that you have to remember that. Under equilibrium condition the number of upward transition is equal to number of downward transition. So what are the upward transition? Only absorption is the upward transition. The stimulated emission and spontaneous emission are downward transition. So we have RAB equal to RSP plus RST. We substitute the values what we have seen in the earlier slides and we obtain a relation for Q. Q equal to this much. And I divide the numerator and denominator by N2 B21 for simplifying, and I supply the value for N1 by N2. N1 by N2 it is e power h nu by kT that we have derived. I am substituting from equation 2. Now I compare this relation with the Planck's energy radiation law, which is given by Q equal to 8 by h nu cube by c cube into 1 by h nu by kT minus 1. So by comparing these two relations we derive the relationship between the probability of absorption and emission processes. So we get first relation is B12 equal to B21. So what it tells, the probability of absorption transition is equal to the probability of stimulated emission transition. So both the probabilities are nearly equal, and from the second relation we get A21 by B21 equal to 8 by h nu by nu cube by c cube, or I can tell A21 is directly proportional to nu cube. What is nu cube? What is nu? So E is equal to h nu. So nu is related to energy. So what is A21? A21 is the probability of spontaneous emission transition, and it is directly proportional to nu cube. Means, so if the energy difference is larger, this spontaneous transition happens more. So if you slightly increase, what happens? So since it is in the cubed power, it will be very, very large. The probability will be more. So these are the things we derive through this study, this derivation. So these three things, A1, A21, B12 and B21, all these three probabilities, they call it as Einstein coefficients. So next we are going to see what are the different types of laser available. So first one is called Nd-YAG laser. So Nd-YAG laser, Nd means neodymium. So they are some chemical elements. YAG, YAG means yttrium, aluminum, garnet. So it is a 4-level laser, and we take the YAG crystal, YAG crystal, and neodymium ions are doped. So we will see. So these are the characteristics of Nd-YAG laser. So it is a doped insulator laser. So we are using optical pumping here, and what is the pumping source we are using? It is xenon flash tube, and the wavelength of this laser is 1.064 micrometer. So let us have a look on the principle. So the principle is, in the yttrium aluminum garnet is doped with the neodymium ions, Nd3 plus ions. So we are making the neodymium ions to excite to the higher level. So through that we can generate a laser beam of 1.064 micrometer. So this is the construction of Nd-YAG laser. So we have a elliptical cavity. So this is the elliptical cavity in which we have a xenon flash tube, and there is a laser rod. So this is the laser rod where we have YAG crystal which is doped with the neodymium ions. On the two sides we have two mirrors. One is 100% reflecting mirror, the other one is partially reflecting mirror. So now what we are doing, we switch on the power supply. So what will happen? So light will be flashed. So the neodymium ions are excited to higher level. So let us see the working of this laser. So what happens? So this is called energy level diagram. So in this case, the neodymium ions are excited to higher levels, E2 and E3. So the neodymium ions absorb the wavelength of this frequency and go to the higher level. So in these levels, they cannot remain in the longer time. So they will come down to the metastable state, that is called E4. So they are coming to this level. What will happen? So this process will happening continuously. So if you observe for some time, so you can find there is a population inversion between the levels E4 and E1. Because I am flashing means more and more atoms go to E2 and E3, they come to the level E4. So after some time, there will be enough atoms in the level E4 to make a spontaneous emission transition. So which will emit a light photon which will induce the other atoms to come down to the ground state. So what will happen? So if this process happens, there will be a chain of photons which will be reflected back and forth. So in our construction itself, we see we are having two mirrors M1 and M2. So these photons, what will happen? So they will be reflected back and forth. So why we are doing means to increase the probability, to make the more neodymium atoms to come down to the ground state. So after some time we have an intense laser beam of wavelength 1.064 micrometer is generated, and it is taken out through the partial reflecting mirror. So these are some of the applications of this Nd-YAG laser. So they are used for communication system, long distance communication system, in endoscopic applications. They are used in remote sensing. So they are find many applications. So next, coming to the carbon dioxide laser. So this is a gas laser. So here the active medium is a mixture of carbon dioxide, nitrogen and helium, and we generate a laser of 8.6 micrometer and 10.6 micrometer wavelength. We get two different kinds of laser through this. So we can quickly go through what are the vibrational states of carbon dioxide molecule. So we know the structure of carbon molecule. So we have a central carbon atom and we have two oxygen atoms. So this is CO2. So these carbon molecule have the property of stretching and bending. So we will see what it is. Symmetric stretching is there. Symmetric stretching means the central carbon atom will remain stationary. Only these oxygen molecules may make movement. So they make movement in the front and back. Okay. So if the first atom is coming closer to the central atom, second is also coming closer. First is moving far away, second is also moving far away. So we use the word symmetric stretching. Second one, bending. Here also the central carbon atom is stationary and the two oxygen atoms, they make a movement up and down. So this is called bending mode. And the third one is asymmetric stretching mode. In asymmetric stretching, what happens? One oxygen atom and carbon atom, they make movement in one direction. Carbon and oxygen, they make movement in one direction. The second oxygen atom move in the opposite direction. So what will happen? So there is no symmetricity, it is asymmetric. Okay. So due to the vibration and bending of these carbon dioxide molecule, what happens? So they have different energies. So these energies or energy levels are used for generating laser. The transition between the vibrational and rotational energy levels leads to the construction of molecular gas laser. So this is the construction of CO2 laser. Here also we are having two mirrors. One is 100% reflecting, the other is partially reflecting, and we have a discharge tube in which we put a gaseous mixture of helium, nitrogen and carbon dioxide. And when you switch on the power supply, what happens? The nitrogen molecules are excited to the higher level. And these nitrogen molecules make collision with the carbon dioxide molecules. So energy is transferred. So carbon dioxide molecules are also excited to the higher level. They make transition to lower levels, emitting laser light of different wavelength, 9.6 micrometer and 10.6 micrometer. So this is a equation which shows how energy is transferred. So initially the electron in the discharge tube collides with the nitrogen molecule. So it is excited to higher level. So the star represents the nitrogen is in the excited state. This excited nitrogen interacts with the carbon dioxide molecule. So the carbon dioxide molecule is excited now, and the nitrogen goes to the ground state. So in this way energy is transferred and we get laser, carbon dioxide laser. And these are some of the applications of CO2 laser. So CO2 laser is used for neurosurgery, microsurgery. It is used for open air communications and in as well as in military field. So next, coming to third and important type of laser is called semiconductor laser. The normal laser pointer we use, it is a semiconductor laser, and its wavelength is 8400 angstrom unit. So let us see how we can construct a semiconductor laser. So we know in a semiconductor we have P-type semiconductor, N-type and N-type semiconductor. We have to make a forward bias, and these kind of semiconductor which are used in this laser are known as gallium arsenide, so which have the property of emitting light. So the energy release which is in the form of light. So this kind of semiconductor we are using, and I am giving forward bias. Forward bias means for P region we give positive charge and N region we give the negative charge. This is the schematic diagram of the PN junction. Let us go to the working. So the energy level diagram we see. So what happens? You can find the free electrons are in the higher level, and the holes in the P region are in the lower level. So when you switch on the power supply, what happens? The electrons from the N region cross the junction and recombine with the holes. So if let us consider one electron here, it combines with the hole by crossing the junction. What will happen? The extra energy of the electron will be released. So this extra energy will be released, which will be taken back and forth. Since the side walls of the PN junction we are highly polishing, so what will happen? More and more electrons make transition to the lower level. We obtain a laser beam of wavelength 8400 angstrom unit. So this semiconductor laser finds application in fiber optic communication. It is used as a painkiller. It is also used as printing and writing CD and reading CD. Here we have listed out some of the applications of laser in different fields. For example, in medical field, for eye surgery. So it is most common practice. So they call it as LASIK. For bloodless operations, laser is used. In industrial applications, for drilling holes, for welding purpose of different materials. Though there are many other applications in each field, we are highlighting few only, one or two examples. Scientific applications, laser is used for communication between planets. It is used for predicting earthquakes. Engineering application, it is used in holography. This holography we are going to discuss. Anyway, holography is a three-dimensional photography. For that, laser is used. For fabricating microelectronic circuits. In military, laser is used for destroying the missiles of enemies, and it is used like radar. So instead of radio waves, these light waves are used, laser waves are used. We call it as LIDAR. And chemical applications, laser is used for accelerating chemical reactions. For creating new chemical compounds are also laser is used. Biological applications, to drill holes, minute holes in the cell walls. Even to do microsurgery in cells, laser is used. Computer applications for reading and writing CD. In laser printers, lasers are commonly used. In communications, most important communication is fiber optic communication. Laser light is used. For underwater communication, between submarines, laser is used. One important application we are going to discuss now, that is holography. So what is meant by holography? It is the art of producing three-dimensional image of an object. So normal photograph, it is two-dimensional. Only X and Y axis is available. X axis will be there and Y axis will be there for normal photography. The third direction, Z direction this projection which is not available in the normal photographs. So this too is recorded, that is known as hologram or holography. So in this image also you can see. So you see a 3D effect of an car image. So light from a source falls directly on the photographic plate. A part of the beam is reflected through a beam splitter and falls on the object, and the reflected wave falls on the photographic plate. So these two waves make an interference pattern. So let us see the diagram. See, here is the laser source. So laser source is here. We are sending some light, laser light. So we have a beam splitter. What happens? So light first directly falls on the beam splitter. It gets splitted. One part is splitted, so I call it as A beam. So A beam directly falls on the photographic plate, and the second beam, say for example B. So B falls on the object and gets reflected. So this is also B beam, falls on the photographic plate. So there will be definitely some path difference. So first A wave will directly falls, B makes a extra travel to the object and falls on the photographic plate. So these two waves interact and they form a interference pattern. They form a interference pattern which is recorded in the photographic plate. So this photographic plate is developed. So this developed photographic plate, we call it as hologram. Now if I want to visualize the three-dimensional image, what I have to do? I have to send a laser light. So through this method, so there is a mirror here. So laser light from the helium neon source falls on the mirror and passes through the hologram. So in this case, we have two images. One is called real image. This one is called real image. The second one is called virtual image. The real image will have the two-dimensional character, while the more interesting 3D effect will be available for the virtual image. So what we have to do? We have to keep our eye here and view through the hologram. I can see the three-dimensional image of the object. So next, we see the different types of holography is there, optical holography and acoustical holography. If you produce hologram through light waves, it is called optical holography. Using sound waves, it is acoustical holography. Holography finds many applications. It is used to store data in the form of a holographic form for non-destructive testing. For non-destructive testing of materials, holography is used, and it is used to study the vibrational objects. So how the object is vibrating, minute vibration, and as well as for identification of fingerprints and for data processing and signal processing. So holography finds many applications. So far we have discussed about what are the fundamental aspects of laser and what are the different types of laser and different applications of laser. So laser finds many applications in various fields, and even it is used in research to invent new kinds of applications. So that is also happening. Thank you very much for watching this. Thank you.